The second speaker this afternoon is Nir Lazarovich from Technion, and he's going to talk about highly twisted knot diagrams.
Thank you, and thanks to the organizers for having me here. It's a pleasure to come back. I've also been to the first instance of this conference. Yeah, maybe I'll start with disclaimers. I'm not a knot theorist, okay? There are better people in the audience, better experts on knot theory than me. And the other disclaimer is that the slides are taken from a colloquium, so for a more general audience than you guys. So yeah, so maybe some definitions will be redundant for you, but nonetheless, welcome. Yeah, so this is a joint work. This is actually based on two joint works, one with Yoav, Moria, and Tali Pinsky, and the other one with all three, Yoav, Moria, Tali Pinsky, and Jessica Purcell. The second one is, maybe I should say in progress, because the paper is not out, is not an archive, and we somehow still find little mistakes that we need to fix. So hopefully what I'm going to say is true. Yeah, some people were wondering what to ask about, and maybe find the mistakes. Okay, good. So I'm going to talk about, this is the outline. I'm going to talk about knots, knot diagrams, then talk about alternating knots, which is maybe the sort of classical setting of what I call twisty knots, see? And then I'll move on to talking about highly twisted diagrams and eventually highly twisted flat diagrams. Yes. Okay, so we all know what a knot is. It's a smooth embedding of S1 into S3 up to an ambient isotopy of S3. Okay, so, and we also know that when we want to represent a knot, what we usually do is take this knot and project it to some plane, and then we get a knot diagram. One of them is, I don't know if you noticed, but it's on the way to lunch. We pass through gates. On one side, you see the Kinoshita Terasaki knot, and on the other, the Conway. It's a mutation of it. It's apparently, again, I don't know anything about knot theory, so I had to Google those things. They appear on the Institute's website, and they explain that it's the knots with the least amount of crossings, such that their Alexander polynomial is the same as the knot, so you cannot distinguish them from the knot. Anyway, so a bunch of knots for you to look at. But of course, the issue is that there are many diagrams per knot, right? The knot, you can take some ambient isotopy, then project, get a different diagram. And somehow maybe the goal is to be able to tell from looking at a diagram what knot it is, or compare two knots. Okay, so we all know probably that one can use Reidemeister moves to go from any diagram to any other diagram of a knot. Yes, this doesn't mean that we can actually describe what are the Reidemeister moves easily, but there is an algorithm to detect whether two knots are the same. Okay, so just looking at their diagrams, it's all work of Haken. So maybe, in a sense, it's kind of, the problem is solved, right? There isn't much to do, but really what we want is to look at a diagram and be able to tell, like, what knot this diagram represents. So here are two examples. Okay, and one of them is the knot, the other one is not. I heard we don't do votes in the UK after Brexit, so we'll not attempt, but no, anyone wants to? Probably, there are experts that can tell.
It's the same diagram. What is the difference?
Yeah.
There's one difference, it's right there. Yeah, okay. No? Okay, so the diagram on the left is the anode. Maybe take this strand and sort of loop it around. And then you see you can move it through and resolve it. And what we'll see about this diagram is that it is alternating. Okay, so it's the first kind of like twisty diagrams that we'll consider. And automatically, just by knowing it's alternating, we'll know that it's non-trivial. Okay, which is already, that's the kind of results we're after. Okay? So having good families of diagrams from which one can actually get information about the knot. Yeah, so here's the goal. So yeah, we want some properties of the knot to be inferred from the diagram. And then hopefully have a unique such diagram in some sense. Okay, so meaning if I was able to produce a diagram of this family, or sorry, two diagrams of the same knot which are from this family, I would want to say they are the same, or to tell when they are the same. Okay, good. So here's the philosophy. So again, I'm not not theorist. This is something that Yoav has like insisted enough around me. So I'm passing it on. The philosophy is that sufficiently twisty diagrams should exhibit more rigidity. Okay, so like families which are sufficiently twisty, that's not a mathematical definition. Okay, should be more rigid. Okay, so we'll talk about two kinds of sufficiently twisty diagrams. One of them is very classical. It's alternating knots. This dates back to Tate. Was actually in Cambridge for some time. And okay, so alternating knots, and the other is K highly twisted. Okay, good. So maybe before we go to knots, let's just do some analogy to get a sense of what we're after. Okay, the analogy will seem kind of stupid. Sorry about it, but the goal is representing rational numbers. Okay, so we know that if you take a rational number, one can represent it using a continued fraction. Okay, for reasons to be cleared later, let me use continued fractions where I put a minus instead of a plus. Okay, and I'm allowing the numbers ai to be in z. Okay, and not in n. Maybe the usual continued fraction for a positive rational number is you put pluses everywhere and the AIs are in n. And we'll see this as sort of an example. Okay, so every rational number can be represented in such a way, but there are several ways of representing the same rational number. Okay, so here's the analogy. We're trying to capture the idea of rational numbers. The tool, the diagram, is continued fractions. Okay, so as I said, this is not unique. There are some kind of relations that one can do on continued fractions. For instance, adding a 0 between two things and adding a 1, 1, 1, and all sorts of relations. Okay, so it's not unique. Here, I mean, the problem is not too complicated, right? I mean, take the continued fraction, compute the rational number, and compare the rational numbers, see if they are the same or not, right? I mean, it doesn't have to be, come up with a whole theory for this. But let's look at two examples. So the first example I'll call alternating, okay, is where the AIs alternate, okay? If you go back to this definition, note that the fact that the alternating sort of cancels with the fact that I put a minus there. So alternating is really the usual kind of continued fractions that you're used to, okay? But let me present them as alternating, okay? And the other family is, I call them K highly valued. I don't know, so it sounds similar to K highly twisted. And this is the family where all the AIs have absolute value at least some k, some number k. And for those families, it's not too difficult to see that if two continued fractions represent the same rational number, Okay, and the continued fractions are either alternating, and okay, one needs to assume some parity on the N and M, or there are 3 highly valued, then actually the continued fractions are the same. Okay, so sort of rigidity of the continued fraction of those. Okay, a silly example, but a good analogy with what's going on. Okay, and after this, maybe let's go back to knots. Yeah, so as I said, the first family of such knots is alternating knots. This dates back to Tate, so 19th century, really the beginning of knot theory. So yeah, maybe let's see the definition. So a knot diagram is alternating if when you follow the knot, you see an overpass, underpass, and so on. Okay, so like this example. I should point here. Okay, so you go under, and then you go over, and then under, and so on. Yeah. So that's something that's very easy to check. You stare at the diagram, you follow like we just did. You can check if it's alternating or not. And let's see some nice properties of alternating diagrams. So the first is non-positive curvature. Okay, that's the only reason why I allowed myself to give this talk in this conference. Apologies. Yeah, so let's just say the knot is hyperbolic if its complement has a complete Riemannian metric of constant negative sectional curvature. Okay, and we know the theorem of Thurston that tells us that a knot is hyperbolic if it's not a torus knot or a satellite. Tell you which one of them. So a torus knot is just you take the standard torus in R3 or S3, and you just draw a curve on this torus. This is the torus knot, and a satellite is something of the following form. You take a solid torus, you take a knot inside the solid torus, a non-trivial knot in the solid torus, and then you take a non-trivial knot. Okay, so this was my solid torus, this is my non-trivial knot, and then what you can do is you can do sort of a satellite construction where you take the solid torus and you place it in the neighborhood of this knot. Okay. So if your knot is not any of those kind of constructions, then we know it's hyperbolic by work of Thurston. And Menasco used it to show that that an alternating knot, okay, which is not a torus, is hyperbolic. Okay, so I missed the assumption prime. Yeah, maybe I'll mention it later. Okay, so here's the. I mean, this is half of sort of what we wanted, which is that the family of diagrams would tell us something about the knot. So in this instance, it tells us about hyperbolicity. Okay. And the next thing is sort of more in the rigidity side. So these are theorems of a bunch of people. So the two theorems I'm going to state are solution to Tate's conjectures. So this is, if I remember correctly, this is the first conjecture. It says that the number of crossings in an alternating diagram is the minimal among all diagrams for such a knot. Okay, this was proved by Kaufman, Moasugi, and Isselthwaite. Who also, I think, was in Cambridge. And the second, which is more in the spirit of rigidity, tells us that just using flipes, okay, so here is a flipe. A flipe is, you just take a bunch of the knot and you twist it to move one twist to another side. Okay, so using flipes, one can take any alternating knot diagram to any other alternating knot diagrams. okay, of the same knot. Okay, so really, if you're presented with an alternating with two alternating knot diagrams, and you ask yourself, is it the same knot? Then you know that you only need to do finely many of those flipes to get from one to that. If they are the same. Good. So this is the result of Menasco and Tissot, and that's the solution of the third Tate conjecture. Okay. Any questions about alternating knots? Good. So now let's switch to the new thing. So the new thing is highly twisted diagrams. Yeah. So for this we need a bunch of definition. The definitions are not about knots, but about their diagrams. Okay. And it's a big difference. Like if I tell you a knot is prime, then you have to look for a sphere somewhere in S3 that you don't know anything about. But if I tell you that the diagram is prime, that's a much simpler thing to check. So diagram is prime if you can separate the diagram itself into two non-trivial diagrams. Okay, along two strands of is it clear? Yeah, so it's something like, I don't know, take a okay. So this is not prime because I can separate it into two non-trivial subdiagrams that are connected by two strands.
When you say non-trivial, you mean that's not just
Yeah, not this.
Yeah, intersections.
Has some crossing.
Yeah, as diagrams, not as knots.
Yes. Yeah. Good. So again, I mean, the point is that it's something you can stare at the diagram and check, or like see. I mean, if it's small enough, you can see it immediately if it's prime or not. Okay. The next one is we want the diagram to be twist reduced. So twist reduced means that whenever you see a situation like the one on the left, then actually the stuff hiding in T2 or maybe in T1 is just a twist. Okay? And it's called twist reduced because you can always assume that your diagram has this form. I mean, if you have such a crossings, then it's either kind of a lollipop, and you can just resolve it. You can reduce the number of crossings, or maybe they are oriented in the same way, and then by doing this flip, you'll just pass all the crossings to one side. Okay, so by repeating these flips whenever you don't see something like that, you'll eventually get to something that is twist reduced. Okay? Was this clear? Okay, good. So twist reduced. And finally, let's talk about K highly twisted. So K highly twisted means that whenever you see a twist, it is followed by at least, there are K of them in a row. Okay, so whenever you start seeing some twist, then there are K such things in a row. Okay? This definition doesn't make much sense if we don't assume that the diagram is twist reduced, just because we can, take any part of the diagram and do this lollipop thing and twist it enough so that it is K highly twisted. Okay, so really one needs to twist reduce it first, and then it makes sense. Okay. So here's the first theorem. So this is a theorem of showing work with Yoav and Tali, but also a version of this existed for the number 6 instead of 3 by work of Futter and Purcell. And it says that if you're given a knot diagram that is prime, twist reduced, and 3 highly twisted, with at least 2 twist regions, then K is hyperbolic. Okay, and those are easy to produce. I mean, you can draw many such things. Okay, as long as you just twist enough everywhere it will satisfy it. Yeah, is it clear?
How you check that it is twist reduced? Because to produce things you can just turn, but you need twist reduced.
Yeah, so you need to look for, I mean, here you needed to look at the sort of curves that intersect twice the diagram. For twist reduced, what you want is curves that intersect 4 times, and moreover that here there is something. And then the question is what's inside. You want to check. So you just go over those. Again, something that you can stare at the diagram long enough, maybe longer than prime, but not too long.
I understood that maybe to be prime for diagram, but not for a knot.
Sorry?
What's the definition of
So prime, the diagram is prime if this was this condition. This is not, diagram is not prime.
No, but then you said that K.
Yeah, this is, yeah, that's
You say in particular.
if a knot K has a prime twist reduced, free highly twisted knot diagram, those are all adjectives that describe the diagram.
Yeah, this I understood, but then in the conclusion you say.
Then,
Prime means.
yeah, in particular the knot is prime.
What does it mean?
The knot is prime means that you cannot separate it into, using a sphere, okay, but you don't know how the sphere looks like. It's not this like simple kind of. Okay, good. And maybe let me say, since we're here, that the number 3 is sort of optimal. If you go to 2, then, okay, maybe I don't have a knot example, but a link example, one can take something like this. Okay, so this is not hyperbolic. For instance, there's an annulus connecting this to that. But it is, you see that it is 2 highly twisted. So here are the twists, and we see 2 in a row. Every time we see 1, we see 2 in a row. Okay, let's maybe talk about, I mean, I'll give you some details of the proof, but, well, not all. Yeah, so we want to show, I mean, following Thurston, we want to show that the knot is not a satellite, nor a torus knot, and the key feature of, I mean, satellite and torus is really the fact that they have either a non-trivial torus inside your knot complement or a non-trivial annulus. Okay. Actually, maybe I should say all of the theorems I'm going to state work as well for links instead of knots. It's maybe simpler to state them for knots. Okay, so if it is one of them, then we can find a non-trivial torus or annulus in the knot complement. Okay, and let's, for the simplicity of this proof, let's just assume that S is a torus. It's a simpler case. So again, so we have some torus S in the complement of our knot, and now we can do the following. So this was done by Menasco in his proof of hyperbolicity of alternating knots. So you can just think of the knot diagram as so around each crossing, put a little bubble, okay, and think of the knot as living on this bubble. Okay, so the overpass is going on the top of the bubble and the underpass is going underneath, okay, like this. Is it clear? Okay, and now we have our torus, which somehow lives in the complement of this knot, and okay, by assuming that it intersects transversely the plane and those bubbles, we can actually assume that the torus, when it intersects each one of the bubbles, it intersects it in a little saddle. Okay, like in this picture, or maybe several of them. It would be a stack of saddles. This one. Okay, and here, so let me tell you where the argument is going. So the whole point is look at how the surface intersects the plane. Okay, it intersects the plane in some curves. And the whole idea of the proof is try to compute the Euler characteristic of the surface by looking at those curves of intersection. Okay? So, yeah, so let's maybe be more precise about what are the planes. So we have the plane P for where the projection is. We have the plane P plus, which is the plane P with the, where instead of taking the little disk here, you take the upper hemisphere of the bubble. Okay? Really, when I draw something like that, I draw P plus, the intersection of the knot with P plus, because we don't see the part that goes underneath. Right? And P minus is the similar thing for the southern hemisphere or lower hemisphere of each one of them. Is it clear what the planes are, P plus and P minus? Okay. Yeah, so now we can, as I told you, let's compute the Euler characteristic. So think of the plane as giving me a height function with respect to the plane. Okay, this gives me a Morse function on the surface. We said that the intersection of the torus with each bubble gives me a saddle. Okay, and outside those bubbles, I can assume that the surface is either a disk that lives above the plane or a disk that lives below the plane. Okay. So really, the computation of the Euler characteristic becomes by Morse theory. It's just the maxima, minima, minus the saddles, which can be seen as the curves of intersection with P plus the curves of intersection with P minus. These are the disks on the top, disks on the bottom, and the little saddles in between. So the number of bubbles that the surface sees. Okay? Are we happy with this? Except for Piotr. Piotr is nodding. Everyone else is like, it's too late for us to actually react. Okay. Good. So you see, it becomes something that we like. We, as in people who do non-positive curvature or that do small cancellation, do this kind of stuff. It's a graph, and you want to compute Euler characteristics. We do all the time. Okay, or at least what I do. Okay, so here's the idea. The idea is you want to compute the Euler characteristic of the surface. You know it's a torus, so you should get the value 0 at the end, right? But here's the idea. Look at the contribution of each one of the curves of intersection to this Euler characteristic, okay? And so you can do a very naive thing. We'll do it later, and try to sum the contribution of each one of the curves to the Euler characteristic. Okay, when you do that, you discover that some curves actually give you positive contribution, which we don't like. Right? We want negative. Right? We're doing not, or at least non-positive, yeah? Non-positive curvature. So here the trick is, whenever you do see something that's positive, try to push it around until it hits something negative and cancels out. Okay? And this is, again, some idea that exists in small cancellation theory. Okay, so that's the idea. For each curve, define sort of a redistributed contribution of this curve to the Euler characteristic. Make sure that what you define satisfies that it's non-positive. Okay? And the sum gives you the Euler characteristic. But then, okay, putting those two things together, we get that each one of them must be 0. Okay, and then what you do is you just analyze all the cases in which you get 0. It's not fun. But you see that, I mean, the curves that give you 0 actually must follow they correspond to a torus that just follows the knot. Okay, so this is a trivial torus. Okay, and similarly, one does it for any lines. Okay, so it's like first 5 pages of the paper, and then, I don't know, 30 is skipped into this define phi prime and so on. Okay, good. Yeah, so the next goal is rigidity. Is really what we want is to be able to tell, okay, if I give you 2 diagrams which are highly twisted, can you tell that they are the same knot or not? Okay, so for this we'll restrict to a smaller family of knot diagrams, which are called flat diagrams. So what's a flat diagram? A flat diagram is you take a braid on 2m strands, okay, and then you just close the top and you close the bottom. Okay, so this is supposed to be a braid, and then the top. Does this have like a? Okay, you close the top with little arcs, and you close the bottom with little arcs. You get a flat diagram. Every knot has such a diagram. It's not too difficult to see. Yeah, it's connected to what's called the bridge number. So from these diagrams, again, you can read something important like the bridge number of a knot. It's related to Hilgard splitting and so on. Okay. Good. So we say that such a flat diagram is K highly twisted if all of the Aij's are greater or equal to K. Note the slight difference between just saying that a flat diagram is K highly twisted and saying that a flat diagram is K highly twisted. So I'm not just asking for it to be a flat diagram and a K highly twisted diagram, but I'm asking it to be a K highly twisted flat diagram, which means that all of those numbers have to be at least 3. Okay? In a flat diagram, originally, those could be even nothing. Like I could just go down like this.
What does the 2m refer to?
Sorry?
A 2m flat diagram, where's the 2m?
M here is 4. It's the number of, 2m is the number of strands in the braid. Okay. So yeah, so the theorem says that if you have 4 highly twisted flat diagrams with certain dimensions, so we need it to be wide enough, so m is at least 4. We need it to be long enough, so n is at least 3. Then the diagram, 2 diagrams that represent the same knot are unique. Well, up to the obvious things, which is you can take the whole diagram and just rotate it like this. It's obviously the same knot, or rotate it like this, same knot, and also the Z. Okay, so let's see how much of the proof of this we can fit in. Okay, so the idea is to use what's called vertical spheres. So this is something that was defined by Finkelstein and Moria, and then extended by work of Wu. So what is a vertical sphere? A vertical sphere is, so first maybe you start with a curve that goes from the top of the diagram all the way down to the bottom of the diagram, okay, monotonically. Okay? And we ask for it to have, in each row of the diagram, to have at least one twist box on its right and at least one on its left. Okay, so the leftmost such curve is shown in red, and the rightmost is shown in purple for the sake. Okay, but there are many such things in the middle, so I drew 2 more in the middle. Okay, so you take such a curve, you close it outside the plane, and this defines an intersection of a sphere with a plane just by putting a disk on top and a disk at the bottom. Okay, and this is what we call a vertical sphere. Okay, and here's the important property of those vertical spheres is that they are very incompressible. So we call those the combination of being incompressible, boundary incompressible, and pairwise incompressible. We call it super incompressible. Okay, so maybe I think at some point I use it in the slides. So should I define what those mean? Maybe I'll define one of them. Okay, so incompressible means that whenever you have, so S. So this is a surface inside a 3 manifold is incompressible if whenever I have a disk. So on this side of the world we write disk with a C. How does it work? D in M who intersects S along its boundary. Okay, so this is some disk that lives inside the manifold and intersects so maybe. Okay, so I have some disk like this that intersects the surface. Then it's incompressible if there exists another disk inside S with the same boundary. Okay, so I can actually close it inside S. Okay, so this is incompressible boundary. Incompressible is a similar thing where you take disks that are half on like the boundary of M, half on the boundary of M.
So, but your surface is spheres?
But they're really punctured spheres, right? Because I take the knot out. Yeah, that's a good observation, right? So the spheres are really punctured spheres. Okay, and finally, pairwise incompressible is the same for, like, if you have a knot going through this disk, you want to find a disk that the knot goes. Okay, but anyway, some nice properties of those surfaces. And I can maybe tell you how you prove this theorem. So the first two parts were done by Finkelstein and Moriah and Wu, okay, for different families of vertical spheres. For the pairwise incompressibility, and actually for the whole thing together, you can use the theorem with the previous theorem about hyperbolicity in the following way. So maybe let's say something about it. So here's your vertical sphere, okay, it cuts the diagram. Here's my diagram. The diagram, okay? Cuts it into two parts. You guys cannot see this. Now let's imagine that it is compressible. So I can find such a disk that does not come from a disk in the surface. Okay, so there's some disk here, okay, that has its boundary on the surface and is somehow non-trivial. So what I can do is I can just double along this sphere. Okay, when I double along the sphere, let's say I double the left-hand side of the sphere, so I get something that looks like the left-hand side reversed. Okay, and the sphere, the disk becomes a sphere. Yeah, just by doubling. Okay, but then what did I get? So one needs to check a bit, but what you get is a diagram that is tree-highly twisted, okay, and satisfies all the conditions of the theorem. So it actually describes the hyperbolic knot. In a hyperbolic knot, I cannot have an essential sphere inside. Okay, and the other cases are done similarly. So instead of a sphere, you get I don't know, an annulus or okay, good. So we know that they are super incompressible. Now what? Now the proof goes as follows. So we have this collection of vertical spheres. Okay, you can think of all of those vertical spheres. And the first step is show that the isotopy that takes one knot diagram to the other takes vertical spheres to vertical spheres. This already aligns quite a lot of the diagram for us. And okay, let's maybe explain briefly how this is done. So, yeah, so that's the proposition. So you consider the image of a vertical sphere. The only thing you know about it is that it is, again, super incompressible. Those are topological properties that has nothing to do with the fact that it was drawn in a certain way on a plane, right? So those survive the ambient isotopy. And then just using this, I should somehow get that it is again a vertical sphere. So let's see how this is done. So again, the idea is use Euler characteristic, okay? So we know what is the Euler characteristic of the sphere. I mean, it's really a punctured sphere, okay? So one should think of 2 minus the number of punctures, okay? Okay, and this can be computed as we did before using this Morse theory, and get that it's the number of curves in P plus the number of curves in P minus the saddles. Okay, and here we also have punctures, so one needs to remove the punctures. Okay, good. And now what? Take this Euler characteristic and instead of redistributing it like we did in the previous theorem, just think of each layer of the plot diagram and what is its contribution to the Euler characteristic. Okay, so for instance, maybe let me do a little sketch. So here's the layers of the diagram. Okay, so for instance, I want to count how many curves I see. Okay, so a curve could go anywhere in this place. Okay, so you see, the curve is now chopped into pieces. They're either going across the layers, or maybe they're doing a little U-turn. Okay. So how do I count how many curves? So maybe I'll just consider, instead of counting the curve as 1, I'll count the arc that gets the minimum as 1/2, and the arc that gets the maximum as 1/2. Okay, and all others will get 0. And what other things? We want to count how many punctures. So a puncture happens when I move between layers. Maybe I'll look at this. Okay, so it looks much more complicated, but when I move between layers, I either move and create a puncture, or maybe I move through a twist region. Okay, so anyway, you take all of those things into consideration and and define those chi-i's. For each layer, what is the contribution of this layer? Okay, good. Now what? Now you work hard a bit. You analyze what can happen in a layer, and you see that each one of them contributes either -1, or at most -1 if it's in the middle of the diagram, or maybe -1/2 in the top or the bottom of the diagram. Okay. But since we know the Euler characteristic of S is, let's say, 1 minus n, okay, and we know that it's also the contribution of each one of the layers, these inequalities show you that it is at most 1 minus n. Okay? So using this, we get that it's exactly 1 minus n, which, by the way, shows that n prime and n are equal. But in addition, in step 3, you show that if it passes through a twist region, then this inequality is strict. Okay? So what we did in step 4 tells you automatically it doesn't pass through a twist region. Cannot be strict. I mean. Okay, so we got some curve that doesn't pass through twist regions. So it must be a very simple kind of curve, and use that to show that it is vertical. Which time do I have? 9 more minutes. Good. Okay, so really the whole point there is step 3. So you analyze what happens in each one of the layers, and you show that that the worst that can happen is what happens for a vertical sphere, and then it must be exactly what happens for a vertical sphere. Okay, good. So now how do we use those vertical spheres to get uniqueness of the plot diagram? So you start with, we know that each vertical sphere is sent to a vertical sphere. Now, okay? So you can start with a maximal collection of those vertical spheres. Okay, so, okay, this is stuff we saw. So you can start with a maximal collection of disjoint non-isotopic vertical spheres in one diagram. Let's say ordered from left to right. Okay, so the leftmost, I don't know if I have it in the, let me go to this drawing. Oh. So the leftmost is shown in red, okay? And then you sort of slowly eat up the twist regions. Okay, so the next vertical sphere would be something that goes maybe from the top and then goes like this. Or maybe like this. It's up to you, decide. Okay, but each consecutive sphere only sees one twist region between them. Okay? If you could see two, then there is another vertical sphere you can pass between them. Okay? Okay, so in particular, you know how many such vertical spheres you see in a maximal collection. Okay, it's basically the number of twist regions, plus 1. Okay, so the first step is you send it to the new knot. You use this the arguments that we saw to say, okay, it's isotopic to a collection of vertical spheres. Even if the first one you arrange in whatever way you like, this new one you don't know much about. Okay, you just know it is a maximal collection of vertical spheres. And maybe up to a rotation, you can assume that they're ordered from left to right, right? So this is where we eat up one of the symmetries that we're allowed to use. Okay, and now between two consecutive spheres, as I said, we see only one twist region. Okay, the pair of arcs that are being twisted, that's a topological property that can be read just by the topology of this. So you know that the isotopy, sends Si prime to Si, Si plus 1 prime to Si plus 1, and it must send the twisted pair of arcs to the twisted pair in here. Okay, but you don't know that they are located in the right place or anything. Okay, so that's a good start. But yeah, and moreover, maybe I should say they have the same number of crossings. This can be seen, for instance, by so maybe closing this on both sides. You see a torus knot of form 2K. But again, a topological property that has to be preserved. Okay. Moreover, if you look at the vertical arc, this vertical arc that goes between the endpoint of the twisted pair to the other endpoint, this must be sent to the vertical arc on the right. And it's again a topological property that one can prove. Okay. And then using the collection of all the vertical spheres, one can extend tree to all vertical arcs. You know that the little vertical arcs that you see there must be sent to, so even, what did I do? Even this little vertical arc must be sent somewhere here to a vertical arc. Okay, and now what do you have? You have a whole bunch of vertical arcs that are mapped to vertical arcs. This tells you that they're either mapped exactly the same or maybe reversed. Okay, so this eats another symmetry. Okay, so yes, good. So then you know that they are ordered in the same way, and you can use that to say that the plant diagram between the leftmost vertical sphere to the rightmost vertical sphere are the same. And even more than that, you can say that the ambient isotopy can be further isotope to be the identity on this part. Okay, so we're done for most of the diagram. We're just left with the little stuff hanging on the left and the right. Okay, so 2 more columns there and 2 more columns there. And here's the idea. Okay, so we know what happens to between the leftmost and the rightmost vertical spheres, and we are left with, let's say, the left part. Similarly, the right. Okay, but as I told you, we know that the middle part is sent by the identity. Okay, so what I can do is I can now connect those endpoints. Okay, let's do that, like this. Okay, and I know that this must be sent to a similar kind of diagram on the other knot. Okay, this is what's called a Schubert normal form for a 2-bridge knot. And what Schubert showed about 2-bridge knots is they can be classified completely using rational numbers. Which rational numbers? Yeah, okay. Exactly the rational numbers that one gets by looking at the continued fractions with a minus sign of the numbers A1, the numbers that appear in here. That's the first number, second number, and so on. So one actually gets two such echelon numbers, okay? One is reading it from top to bottom, and the other is reading it the other way around, okay? Which makes sense because the two bridge knots are the same up to flipping them, right? Okay, so but this pair of echelon numbers completely describes the two bridge knot. And what we saw, okay, so this is the theorem, completely characterized by those numbers. But what we saw is that at the beginning is that if those numbers are at least 3, okay, we're even assuming that they're at least 4, then the continued fraction is unique. So actually know that the numbers a, 1, 1, so on, and up to a and 1 are the same as the prime. Yeah, the same is done. I mean, okay, I'm hiding a little detail here that one should still tell if it's going from top to bottom or bottom to top. Okay, some extra argument needed there, but that's basically it. You do the same for the rightmost part of the diagram, and you got yourself the proof is complete. Yeah, so thank you.
Questions?
So in the flat argument, is it possible if you take any super incompressible punctured sphere with meridional boundary slope, it's isotopic to one of the vertical spheres?
Sorry again?
So in the flat argument, so if I give you any super incompressible sphere with meridional boundary slope inside the known exterior, could it be isotopic to a vertical?
So there was a little thing there that I maybe didn't mention, is that you need to know how many punctures it has, right?
Right.
So we do use the fact that it has at most n+1 punctures, and then you know that it must be a lot. You're asking if for any number of
Yeah, but you've answered the question.
yeah, okay. Let me do your thing.
What's on the last slide?
What? What's on the last slide? Yes. Good. Yeah, so let me use this to advertise a conference we're organizing for Micha in Lumini next May. I hope the QR code works. Let's see. People are testing.
Yes.
The website contains a list of speakers that should still be confirmed. Contains photos that I stole from all around the internet. But anyway, registration will only open in September. But I think this is the right crowd to also attend this kind of conference. It will be about Q complexes and ideas around. Did it work? Did the QR code?
Yes.
Okay. Should we clap again?